Imagine gazing up at the vast tapestry of stars on a clear night. Although the seemingly boundless cosmos appears filled with glittering lights, what we see is only a small fraction of what truly exists in the universe. Beyond the familiar stars and galaxies lies something mysterious and invisible. Physicists call it dark matter and dark energy, and they believe these hidden components outweigh every atom, molecule, and speck of cosmic dust we can directly observe. To understand dark matter, we must first explore how galaxies spin. Decades ago, astronomer Vera Rubin discovered that stars on the outskirts of galaxies revolve as swiftly as those closer to the galactic center. According to the laws of gravity, if only visible matter were holding these galaxies together, the stars along the edges should have been flung outward, much like children drifting away from the center of a merry-go-round when it spins too fast. Yet they stayed put. This unexpected observation hinted that an invisible, gravitationally powerful substance must be providing extra mass to bind galaxies together. Scientists dubbed this elusive material dark matter. By dark, we don't just mean it's black or hiding in the shadows. Dark matter does not emit, absorb, or reflect electromagnetic radiation, making it effectively invisible. We only know it exists through indirect effects, like the way its gravity bends light from distant galaxies in a phenomenon known as gravitational lensing. Physicists are still searching for particles that could form dark matter, including intriguing candidates such as WIMPs, or weakly interacting massive particles, and axions, hypothetical particles that, if found, might explain how dark matter interacts so little with everyday matter, and yet has such profound gravitational influence on cosmic structures. Scientists across the globe are pushing the boundaries of technology to find traces of dark matter. Deep underground laboratories are home to detectors designed to spot the faintest signals from passing dark matter particles. Upgrades at CERN, home to the Large Hadron Collider, aim to generate higher energy collisions that could create or reveal dark matter particles under controlled conditions. Meanwhile, astronomers look to the skies for clues. The European Space Agency's Euclid telescope, launched to map the geometry of the universe with unprecedented precision, will help researchers trace the subtle effects of dark matter on galaxy clustering. The Vera Rubin Observatory, set to conduct a decade-long legacy survey of space and time, will gather a vast trove of data on billions of galaxies, allowing scientists to track the gravitational fingerprints of dark matter with extraordinary detail. Each of these projects offers a unique lens into dark matter's elusive nature. While dark matter is the invisible glue holding galaxies together, dark energy is an entirely different and even more mysterious component. In the late 1990s, two independent teams of astronomers studied distant supernovae, powerful explosions that signal the death of massive stars, hoping to measure how quickly the universe's expansion was slowing down. Instead, they discovered a bombshell. The expansion of the universe is not slowing at all. It's accelerating, driven by some strange energy embedded in the fabric of space-time itself. This repulsive force has been labeled dark energy, and it appears to account for most of the energy content of the cosmos. If current models are correct, only about 5% of the universe is made of ordinary matter, the kind you and I and the stars are made of. Dark matter makes up roughly 27%, while dark energy dominates at close to 68%. Think of it this way: everything we can see and touch is almost inconsequential on cosmic scales. The bulk of our universe is made of something for which we have few direct clues. Scientists have proposed several hypotheses for both dark matter and dark energy, although neither has yet been definitively pinned down. For dark matter, one of the leading ideas focuses on theoretical particles called WIMPs, weakly interacting massive particles. WIMPs would interact via gravity and the weak nuclear force, but not electromagnetically, which would explain why they're so difficult to detect. Another compelling possibility is a very light particle known as the axion. Axions arise from certain extensions of the standard model of particle physics, and could account for the large amounts of missing mass inferred from galaxy rotation curves and gravitational lensing observations. Other proposed dark matter candidates include sterile neutrinos, hypothetical neutrinos that do not interact via the weak force. and even exotic possibilities like primordial black holes. For dark energy, the simplest candidate is the cosmological constant, a tiny, constant energy density permeating all of space, first introduced by Albert Einstein, and later revived to explain the observed acceleration of the universe. This idea suggests that the very vacuum of space itself has an intrinsic energy. Another possibility is known as quintessence, a dynamic, evolving field that changes with time and space. Quintessence would behave somewhat like the Higgs field, influencing the expansion rate of the universe in ways that could vary over cosmic history. Some scientists also explore whether modifications to our theory of gravity, rather than an exotic form of energy, might account for the acceleration. None of these ideas have yet been confirmed, making dark matter and dark energy two of the biggest open questions in modern physics and cosmology. Physicists and astronomers continue to seek answers. From upgraded particle accelerators on Earth to advanced space telescopes and observatories peering into the furthest reaches of the cosmos, we are inching closer to understanding these profound cosmic mysteries. No one yet knows whether our current theories will hold or be overturned. But the very quest to understand dark matter and dark energy is one of the most exciting frontiers in modern science. By chasing these invisible forces, we hope to unveil the deeper architecture of reality and perhaps discover realms of physics that lie far beyond the shadows of the known.